Okay, so we are in Chapter 3, questions 13a through 13j of An Introduction to Statistical Learning. This video will be done in R, and I will make a separate video for Python. With these multi-part questions, it doesn't make sense to read the questions really, and so we will just kind of start jumping in. So the first part, part A, we're going to use the rnorm function to create a vector called x of 100 observations, and x will be distributed normally with a mean 0 and standard deviation 1. Okay, and that's what we have right here. So I run that. Okay, so again, I use the rnorm for random of a normal distribution. I want 100 observations of a mean 0, standard deviation 1. Okay. Now we want to make a separate normally distributed vector with 100 observations, this time called EPS or epsilon. So epsilon is this little character here, and it's often used to signify error in these linear models. And we want it to be in, and this gets a little bit tricky, so it's 0.25. A variance is 0.25, but in R it uses standard deviation instead of variance, and so the standard deviation is the square root of the variance. So this gets us the appropriate value. Okay, but I just use the same command as before. Okay, calling it epsilon or EPS. And now in Y, I'm going to create a variable y using x and epsilon, and y is going to equal this right here, right? So -1 plus 0.5x plus epsilon. Okay, so I just plug that in here. And it asks us what is the length of vector y. Okay, so I'm going to get that with the length y function here. And it asks us what are the values for the intercept, beta naught or beta 0, and the slope of x, beta 1. But those are just in these are just in the definition of y. -1 is the intercept, and beta 1 is 0.5. Okay. So now we're going to create a scatter plot of the y we've created with the x, and then I'm going to use the line that I've implied here with my intercept and slope term, and I'm going to plot that over top of everything, and this is what I get. Okay. It asks us to comment on what we observe. I'm not really sure how to answer very open-ended questions like these, other than to say that the line seems to fit pretty well. But that's by design. So anyway, okay. Part E, we're going to now fit a least squares regression of y onto x, and then we're going to compare the estimated values of b0 and b1 to the assigned values of b0 and b1. Now, if that doesn't make sense, remember that we made x and epsilon to define y, and both x and epsilon are random variables, and so we can predict what they are within a distribution, but we don't know what the exact values are going to be, right? And so even though we've assigned beta naught and beta 1 to be these values, because of that randomness in x and epsilon, a regression may not reveal exactly those values. In fact, it probably will not reveal exactly those values. Okay, so here I have, I'm running my model. I'm using my LM function, which is R, regressing y onto x, and I'm looking at the summary. And if I go here, I can look at the intercept, which is close to -1, but not quite. And I get my value for x. Again, it should be 0.5, and it's a little bit over that. So the beta hat, the estimates for the beta values are close to, but not exactly the ones that the values that we assigned. Okay. And so now I'm going to plot the data once again, and I'm going to put both lines on there. I'm going to put the assigned value line, okay, and then what the regression finds. Okay. It also wants us to add a legend, and that's what I've done with this legend command here. To use that, you say what's the first thing that it's showing? It's the assigned values and the estimated, so I'm calling them those things. Red matches the AB line for red, blue matches the AB line for blue, and the line type's 1. The line type here, LTY, it's assumed to be 1, I just didn't put it in there. And then line type for this one is 2. Okay, and so then it gives you the key or the legend up there. Okay, and so again, here we have the assigned regression line and then the fitted regression line, okay? And we see that they're pretty close, but not exactly, and that not exactly the same falls out of the fact that the estimates for the beta values were not exactly the same. Okay. So now we're going to fit a polynomial regression of y onto x as well as x squared. And then we want to know, is there evidence that the quadratic term improves the model fit? Okay. So here I have my regression with the polynomial, and to add a polynomial you can do it in a lot of different ways, but the way that I'm choosing here is to use the poly command, x and then 2. So this gives me a second order, so give me a first and second order polynomial for the variable x. And then I have the summary of the previous regression shown up here, as well as this new regression, and so I'm just going to look at that. And so just to demarcate this for your eyes, this is for the first model and this is for the polynomial model here. Okay. And we want to know, is there any evidence that adding the polynomial term improved the fit? Okay. And it depends on what we mean by, well, in this case, it may not depend on that. But in general, whether or not it improves the fit depends on whether we're talking about the in-sample fit or the out-of-sample fit, the training data fit or the test data fit, okay? So whenever we're adding terms, right, we're adding an x squared term here, in general, we're going to improve the fit to the in-sample data, okay? But that may not be the case for out-of-sample data. Again, this is the variance and bias thing that was talked about in earlier chapters, okay? So whether or not this improves the fit or not is, well, again, it depends on what we mean. Do we mean to the data or do we mean to the out-of-sample data, okay? But what would we use, just given these printouts, to start to assess that? Well, if we were looking for in-sample data, the things that we would use just in these printouts would be things like residual error. Okay, there's residual error. Right? And we notice it's slightly lower in the second model, which we tend to expect, right? Because we have more terms here that can fit the data. Okay. So on the training data, the second one so far seems to be performing better than the first one. We can use r squared or multiple r squared. Okay, and we see in the second one it's a little bit higher, which again we expect if we have more explanatory variables. Okay. And I guess we could also use the F statistic, okay, in here, in which case the first one seems to be performing better than the second one. The F statistic is taking into account the degrees of freedom, right? So because we have one more term here, we have one fewer degrees of freedom here, and the F statistic is taking care of that. But we could also compare the two models using something like, I think I put it in here somewhere. Using ANOVA. And if the two models are significantly different, then we could say that one model was fitting the data better than the other. When you run it on these, just to go ahead, it does not show a significant difference, and so you might say that there's no evidence that the polynomial term improves the fit. I don't know if it's fair to say that there's no evidence. It's just that according to the logistics of p-values, there might not be any evidence given by that particular test. Okay, but again, there's a test here that seems to suggest that there might be. There's a test here that suggests that there might be. Anyway, and for out-of-sample fit, really the one that we probably would use within this printout is the adjusted r-squared value. Again, with more terms, we should see a better. Well, I'm sorry. With more terms, we should see a better multiple r squared. But when we're adding terms, we can adjust for possible overfitting by accounting for the number of terms that we're using, explanatory terms, and that's adjusted r squared. And we see that in this one, the second model performs slightly better. I mean, these are all slightly. In all, I would say that the second model is not really performing much better than the first, right? Because all the ways in which it's better are just minimally better. Anyway, okay. So now for part H, we want to repeat everything that we just did, but now instead of the epsilon term having a standard deviation of the square root of 0.25, which is 0.5, we want to tighten it up a little bit. And so I'm using a standard deviation of 0.1 instead of 0.5. Okay. And so we're going to go through and basically repeat everything. So, all right. So we'll get to the figures here in a second. But so here we have the first model, okay, and then the polynomial model, and we can go through the same. We can go through the same thing. In this case, we see that the adjusted r squared is better for the simple model compared to the second one, okay? Let's see, what else might we want to look at here? Well, we can go through the same things, but once again, it does not seem that the polynomial term is really contributing much of anything to the fit here. But of course, it shouldn't, because we made the data to not have a polynomial term in it, so we shouldn't really be surprised by that. Okay. So I'm also going to plot these just to show you what's happening. So this was the first data set right here, okay? And now this is the second one, right, with the tighter epsilon term, okay? And so you can just kind of see how the data bunches together here. All right. Okay, part I. Now we're doing it again, but now we are loosening the epsilon term. So I'm having a bigger standard deviation for epsilon. I'm going to go through and do the exact same thing once again. I'm going to get rid of that set.seed term there. I haven't been using it. Did I get rid of it up here? I did not. I don't like that. Okay, anyway. I'm just getting rid of these, even though the question suggests that we use it. Okay, but I'm going to go through, do the exact same thing. Again, here is the simple model. Oops, not quite. Here's the simple model. Here's the complicated model with the polynomial term. And we can go through once again, comparing the adjusted r squared values, which is maybe our, and maybe F statistic, are our best indicators of out of sample fit. And we see that the first one is actually doing better on both of these. In sample fit, unsurprisingly, it seems that the second one, the more complicated one, the one with more terms, the more flexible one, is maybe performing slightly better. But again, probably not a lot of evidence that the polynomial term is adding much of anything. Now looking at each of these, okay, so this was the first model we looked at with standard deviation of the epsilon at 0.5, 0.1, and now 1, so the biggest standard deviation. You see how the data starts to spread out as we go through all of these, okay? But the regression line is remarkably similar in each instance, okay? The extent to which they vary is the extent to which the random term, the epsilon term, is being varied because of the increased standard deviation. Okay, and finally, we want to look at the confidence intervals. Oh no, I did it for y, not for the beta terms here. Oh no, I did. Never mind. Sorry. So we have the confidence intervals for beta naught, which is the intercept, as well as beta 1, which is x, for our three models. Okay, so let's just look at what's happening to the to the confidence intervals for x, which is the beta 1 term. We can also, well, I guess we can do it for both. But we should see that as the epsilon term gets more variable, the confidence intervals get more variable, of course. So here we have the middle of the pack. This is the first model we ran where standard deviation was 0.5 on the epsilon term. Okay, so we can look at those. And then the second model is where we tightened it up. And notice that this interval from 0.48 to 0.51 is less than this interval. And then we had the model where the epsilon term had the biggest standard deviation, and lo and behold, we have the confidence interval is the greatest, okay? Greater than either of the other two. Okay, so I think that takes us through this marathon of a question, and I will call it good there.